right? With hypothesis testing, we've worked through examples where we have a sample mean and we have a known population variance. Didn't seem very likely. We then also looked at examples where we have proportions. Those two situations, we always use the standard normal distribution, right? If I have a proportion example, standard normals or z-tables. If I have a sample mean, but I know the population variance, standard normal z-tables. The only time we start to use those student t-tables like we did for confidence intervals is if we only have a sample variance and we have a sample mean. Right? So what are the steps going to be to do hypothesis testing for that scenario? Well, same thing, identify the null alternative. We still need to know what alpha we're testing at, right? What confidence level or significance level. The kind of different step now is if I want to find critical values, those, remember before, my critical values were coming from this standard normal or the z-tables. They represented z values. Now my critical values, I know that when I only have a sample variance or I don't know the population variance, I'm going to have to use the student t-table, so there'll be t values instead of z values. So I still find them the same way. There's still going to be the values that give me alpha in whatever tail I'm looking at, right? And it's still, right-tailed test, positive critical values, two-tailed test, negative critical values, two-tailed test, pairs of critical values, remember we said? So we'll make sure we do a two-tailed example here soon. But then the other thing that's going to be a little bit different is my test statistic equation. It looks exactly the same, other than instead of my population variance, I'm plugging my sample variance in there. That's the only thing that's different, right? So, once I plug the numbers in, my test statistic looks no different than it did before when I'm looking at sample mean examples. Now, just some kind of clarification. So this is still a test statistic, but I probably will now refer to this as a t statistic, right? So it's a test statistic coming from the student t distribution. Remember when we said a z statistic, that's a test statistic coming from standard normal distribution, right, or the z-tables. But other than that, once we have the critical value in the test statistic, we plot our critical values, draw our rejection region. If the test statistic's in our rejection region, we reject. We could do the p-value approach here as well. I likely, I shouldn't say likely. I would not ask you to find p-values on the exam kind of for when we only have a sample variance, and I'll show you why once we start working through some of these problems. Right? We still could do it, but for at least this exam, I wouldn't expect you to. So really the steps haven't changed. Steps haven't changed much. So let's say we want to test for whether or not the average home value in Muncie is different than 90,000. Okay? So right away we should know what type of tailed test do we have here. Yeah, different than means not equal to, right? So what I'm trying to do, or what I'm trying to test for, I guess I should say, my alternative hypothesis, what I want to test for is that mean anything different than 90,000? So for my null, I assume the opposite is true, which is that it's equal to 90,000. So when you see this term different than, hopefully these are like easy null alternative hypothesis to identify. So we know we've got a two-tailed test. And just the other information that we're told, we find a sample mean of 85,000. I looked at 51 homes, and my sample variance is huge, so 100 million. Probably give you a number a little bit easier to deal with maybe on the exam than that. So we've got a two-tailed test. What are our critical values going to be? Okay. Well, what we're thinking about doing doesn't look, hasn't changed from the examples that we were looking at before. However, instead of a z table or standard normal distribution, I'm looking at a student t distribution. So what I want, right, is a critical value, but here I have a two-tailed test, so it's going to be a pair of critical values that give me alpha total in the tails, or alpha over 2 in each tail. Okay? So let's, I think I asked for 3 different alphas, but let's just do the first one. So alpha of 0.1 over 2 is 0.005, not 0.005, 0.05, right? So I want 0.05 in each tail. When I ask you for 3 critical values, it's actually a little bit easier when we have a student t-table distribution. Because now, if I go, first of all, if I gave you a question like this in the exam, this is really kind. Why? We're dealing with a two-tailed test here, so I know I've got pairs of critical values. D has to be the right answer. But how did I get these values, right? So even though we know D because of that very raw principle that for a two-tailed test, we have to have pairs of critical values. How did I get those? So if I go to my student t-table, well, what I'm going to do is say, okay, look, what was my sample size? I think my sample size here is 51. So my degrees of freedom would be what? Degrees of freedom is simply n minus 1. So 51 minus 1 is 50. So if we wanted to do that ahead of time, we could have. So I've got my degrees of freedom of 50. The area that I want in the tails, right, alpha over 2. So I said 0.05, right? That was alpha over 2, 0.1 over 2. So I go down here to my degrees of freedom of 50, 1.676. The next one was an alpha of 0.05. Well, it's a two-tailed test, so it was alpha over 2, so 0.025. Go down to degrees of freedom 50, it's right there. And then the last alpha of 0.01, well, half of alpha is in each tail, so 0.005. Down at my degrees of freedom of 50, here's my critical value. So I've got, my critical values 1, 2, and 3 right here, right? Because I identified that degrees of freedom, and then it was just what area do I want in the tails, right? Now, it's a little bit trickier with a two-tailed test because when I say what area do I want in the tails, well, I want alpha total, but in each tail, right, I've got alpha over 2. So I had to look up alpha divided by 2 of those 3 different alpha values. So 0.1, 0.05, and 0.01, two-tailed test, divide those by 2, right? Because half of alpha is in each tail. So I need the values that give me half of alpha in each tail. So 0.05, if I think about my alphas were 0.1, 0.05, and 0.01. Well, I divided those by 2. That's the area I need to look up. I've got 0.05, 0.025, and 0.05. So those are the columns I looked at on the student t-table at my degrees of freedom of 50. Okay. Now another thing, I think I mentioned this last class, but if we did have an example where we wanted to use the standard normal distribution, it's also kind of nice to use this. So before, like when you asked me earlier, how did you get the 2.33? Well, didn't show you, but then we went back and you have to use the standard normal table. But remember, this last row in the student t-table, these are my standard normal distribution values. So I could have gotten that 1.28, 1.645, 2.326. Those are the same values as earlier, but they were all rounded to the second decimal, 1.29, 1.65, and 2.33. Right? So you could use this last row to kind of get even a more accurate value for that standard normal out to the third decimal. But for this example, we only had degrees of freedom of 50, not an infinite, right? Or we weren't using kind of a standard normal. So that's how we were grabbing these 3 values. Okay. Any questions on that before we keep going here? Yeah.
So you were looking at the alpha divided by 2 to grab those values?
Yep. So when I was looking up here, the column headings, and I said this when I first introduced the student t-distribution, you can cross this alpha off if it confuses you. These column headings are simply telling you the area in the upper right tail. So you know that you have 2 tails, but you know that the area that you want in each of those tails is alpha over 2. So those were the values you looked up, 0.05, 0.025, and 0.005. Yep, you're looking up the area that's in each tail if you have a two-tailed test. Yep, it's a good way of saying it. And then, of course, we had to go all the way down to what our degrees of freedom was. So kind of the tough part about these student T examples is that the critical values are going to be different depending on your degrees of freedom. Before it was kind of nice. We were seeing the same 3 critical values all the time for left and right-tailed tests and for two-tailed tests. Right? It's going to be always the same 3 when we're using that standard normal distribution. But when we use a student T, right, depending on the degrees of freedom, those critical values will change. Okay. All right, so we've got our kind of critical values there. What would the test statistic be? Okay. Well, if I look at this, I mean, the variance is kind of high, but seeing a test statistic like this would mean that I pretty much found a sample mean that was really, really close to the population mean, right? Because the test statistic, even if it's a t statistic, is still telling me something about the number of standard deviations away from the mean, okay? Well, the number of standard deviations being away from the mean is 0.002. That means I'm pretty much at the mean, right? I'm like almost no standard deviation. So I'm going to probably guess it's A or B here. And then one thing that you can kind of help you on the exam, I guess, with these multiple choice questions. So before we get too lost in what we're doing, if we just simply draw out, okay, well, what would the distribution of my sample means look like? I've assumed from my normal alternative hypothesis, right, that population mean is 90,000. So if in what I assumed to be true was in fact true, my sample mean should be normally distributed around that. I then found a sample mean of 85,000. So when I think about converting this to my t statistic, right, I saw something below the mean, so I should have a negative test statistic, right? Because that test statistic is still a z or a t value, and it's telling me how many standard deviations away from that assumed true mean I am. Well, if I see a sample mean below that assumed true mean, I'm going to be a certain number of standard deviations below or negative. Right? Now, how do I actually kind of find what the value is? So probably negative 3.57 would have been like the best guess there. If I want to like make sure that I can calculate this test statistic, it's just like before. Take the sample mean, you subtract the assumed true mean. It's just now we're dividing by the standard deviation of our sample means that is only using the sample variance, not a known population variance. All right? But from here, it's just what? 90K minus 85K over square root of, I think it was 100 million. And then my sample size was 51. So remember, when you're calculating your test statistic, you're not using degrees of freedom here, you're using your sample size. The degrees of freedom is only identifying, which of those distributions you're using when you're looking at things like critical values or p-values. So I think if we enter this into our calculator, we should get that negative 3.57. Okay. Any questions or anything up to that point? Now, we had those three critical values from earlier. We could have plotted them, but notice, so I've got positive and negative, these were my three different levels. My test statistic, if I draw this out, it's going to end up being in the rejection region because negative 3.57, right, is greater in absolute value than all three of these critical values, right? It's going to be kind of out way further in the tail and going to be in the rejection region at all these levels. All right, so for the sake of time, I'm not going to kind of draw out that again, but we'll work just more examples where I find the critical value and kind of plot those. But here, this one was a little bit easier to see. I mean, my critical values are at the most 2.68, and I found, or sorry, negative 2.68, and I found negative 3.57. That's going to be way further out into the tail or way more extreme. So I can clearly reject it all three levels here. Now, the critical value approach is usually how we're going to have to approach these problems because we run into a problem if I try to calculate the p-value. So remember, the p-value is the probability that I see something as far away as I did from the assumed true mean or even further that goes against the null. Well, here, remember, if we go back, we had a two-tailed test. So this actually only represents half the p-value. It would have been equally as likely for me to see something 3.57 standard deviations above the mean or further, right? So the other half of my p-value is in the other tail. So if I could find this area, I could then multiply it by 2, and that would give me my total p-value because I know that there's two tails of equal size. So I go to my standard normal table. I've got negative 3.57. I've got two issues. So one is that when I'm looking at the student t table, it's only looking at that right side of the distribution. So everything's positive. Well, I could actually recreate the exact same table and think about the left side of the distribution. All the numbers would be the same. It's just that they would all be negative because this is still a symmetric distribution. So I can still look up values here. Like let's say, I have what, negative 3.57. Well, I'm actually going to be looking for the test statistic of 3.57, right? Then I would kind of look and say, so for example, if my degrees of freedom was 32 and my test statistic was 1.309, the area to the right of 1.309 is 0.1, right? So I can look up my test statistic at this degrees of freedom and then find the corresponding area in the tail. The problem is if I go down to my degrees of freedom of 50, I don't see a 3.57, right? In fact, it only goes up to 2.678. So what's the area to the right of 3.57? Well, if the area to the right of 2.678 is 0.005, the area to the right of 3.57 is just going to be something smaller, right? So if I'm thinking about what I'm doing here, stop dropping my markers. When I look on that table is telling me that the area to the right of 2.6, I don't know if it was 5, it was 2.68 maybe. The area to the right of that was 0.005. Well, that means I know the area to the right of 3.57 has to be something smaller. But I don't know exactly what it is. All I can really say here is that the area in each one of these tails is less than 0.005. So the total area, right, if each tail is less than 0.005, if I add those together, I can say that the p-value is less than, what, 0.005 plus 0.005, which is 0.01, right? But that's all I can say, and I can only put kind of bounds on my p-values. So that's why on this exam, and we'll kind of determine we can actually find, bound our p-value and still use that. And we'll do some more hypothesis testing after the exam. But for this exam, I won't ask you a p-value question where you only have the sample variance because you're only going to be able to put bounds on it, and we haven't gotten a lot of practice with kind of this, so I don't want to throw another wrinkle in there. But this would be how you would do it. Right? But we can very easily do the critical value approach, right, which is what we did here, right? We found our critical values, we found our test statistic. We could plot that against our critical values and determine if we reject or fail to reject. Okay. Questions on that before we keep moving? I think I've got one more example that we'll work through by hand, and then I'll probably kind of show you some stuff in Excel. But at the same time as I'm doing Excel, I'll be doing it by hand as well, okay, to kind of hammer down this idea. So let's say now we've got this example where we want to test for whether or not the birth weight of babies born in Indiana is less than the national average of 3,287. Okay? So what we want to test for is our alternative hypothesis. So alternative hypothesis is this mean less than the national average of 3,287? We assume the opposite is true, which is that it's greater than or equal to 3,287. Okay. So what type of tailed test do we have here? Well, we have a less than sign. So we've got a less than or a left-tailed test. Just some other thing we were told, the sample mean we found was then 3,132. Our sample size was 400 births, and our sample variance was some big number, right? So we just write that down, what we were given, just to make this easier. Well, we already identified the null alternative here. So we've got this left-tailed test. Right? What will the critical values be? Okay. So this one I'll plot out for us. So what I want to find, right, and I can start out with an alpha of 0.1. So I want to find the critical value for having 0.1 in my left tail. Right? I've got a left tail test. So what's the critical value that gives me 0.1 in that tail? I would then kind of, well, I could think about, here's my rejection region. So what's my degrees of freedom here? Well, it's actually pretty large. And here's another one that kind of presents an issue for us. So I got degrees of freedom of 399. Well, if I go to that table and I try to find a degrees of freedom of 399, I got a problem, right? I start having big jumps here. I could do this in Excel, but my table is kind of limited, right? If I went up by 1 all the way up to 1,000, my table would be way too big, right? I couldn't even store it in my backpack or whatever. So if I've got 399, if I use the degrees of freedom that's closest to it here, we'll just assume that, that's going to be the closest. So we'll use 500. Well, then what I would do to find my critical value is, okay, at that degrees of freedom, I want 0.1 in that tail. So I scroll down, 0.1 in the tail at the closest degrees of freedom, 1.283. Now the issue is 1.283 is actually not my critical value, right? It's kind of, because our student t-table only looks at the right side of the distribution, if I want to look at the left side of the distribution, it'll give me the value, right? 1.283 is the right value. It's just that for a left-tailed test, my critical values are negative. So when it comes to using the student t-table, you can use it to find the values, but then you're really going to have to remember that depending on what type of tailed test I have, if it's a left-tailed test, it's that value, but negative. Okay? Right-tailed tests are a little bit easier using the student t because it's looking at the right side of the distribution. We could then do the same thing. What's the critical values that give me 0.05 and 0.01 in those left tails? Well, when I was on that table, it would have actually been pretty easy. I want 0.1, 0.05, and 0.01. Those are my 3 alphas. That's the area I want in the tail. So I go down here. It's going to be 1.283, 1.648. Remember, I have to make them negative because I'm looking at the other side of the distribution. And then 2.334, so negative 2.334. Okay. But now I've got all 3 of my critical values, and I can think about, there's my rejection regions. Okay. Does that make any questions on that? Yeah. So you don't have to if you don't want to. We said, okay, so good question. I'll answer here in a second. Any other questions for, yeah.
What does it mean that they're negative? Because you said you have to remember on the left side when you do left tail test, it's going to be negative, but what does that mean or signify?
So remember, these values represent the only evidence. So it's like saying, if I see sample evidence that's more than 1.28 standard deviations below what I assume to be true, then I can reject, then I'm okay rejecting. So the problem is with a left-tailed test, the only evidence that goes against the null is evidence on the left. So I'm going to have to set my threshold to be a certain number of standard deviations below or negative critical values. Okay. Whereas on a right-tailed test, only evidence on the right side or above a certain value, I could reject the null. And so there I have to be a certain number of standard deviations above that assumed true mean when I'm setting my threshold.
Okay, that makes sense.
Yep. Okay, good questions. So I'm going to calculate my test statistic. I'm not going to write the whole equation out again. I'll show you on the formula sheet here in a second where this is at. But, we have the format here, and I put Z. That was wrong, right? We only have a sample variance, so I'm using a student T table, so I have a T statistic. So I've got my sample mean minus my assumed true mean. So I go up here, got those values there. So 3132 minus 3287. And then I'll divide by the square root of my sample variance divided by my sample size. So 439,907 over 400. Okay. So that will give me my test statistic. Okay. Yeah. It's okay. 390. Oh, up here. So the way so our degrees of freedom is helping us identify what student T distribution we should be using, because there's truly every single different sample size has its own student T distribution. The reason why we do degrees of freedom, so think about it this way, we can't have a degrees of freedom, we can't have like you could replace degrees of freedom here and simply do this as the sample size and it would just start at 2. Because if you go lower than a sample size of 2, you just grabbed one observation, you're back to just the distribution of the data. So it relates to some things that if we were to kind of continue, I mean, we'll talk about it once we get to regression, but degrees of freedom start to become more complicated when we start to develop more complicated statistics. And so we'll start using the terminology here, and it makes a little more sense once we get to something like linear regression. But the idea was that we've got a sample variance, so dividing by n-1 is going to influence how much our student t-distribution varies from the standard normal. Because when n is large, dividing by 1,000 instead of 1,001 isn't that much different than, or sorry, isn't that much different, but dividing by 3 instead of 4 can make a much larger difference. Yep. All right, so I have to check here because I can't remember what this works out to be. So we get our test statistic, it's negative 4.7, we'll call it, just to make it kind of easier to write. So approximately negative 4.7. Well, this is kind of an easy one because where would that be? Somewhere way over here, right? You know, negative 4.7 is going to be way, way out here, which will clearly be in the rejection region at every single level, or at every single level, 10, 5, and 1%. Okay, so when I start seeing test statistics that are over 3, I should start to be thinking, okay, my rejection decision is going to be reject. It doesn't matter what, you know, alpha I'm looking at, my critical values never kind of get out as far as 3. If I'm more than 3 standard deviations away from what I assume to be true, then it's probably not the true mean, right? So that was a scenario we had here where we had a pretty extreme test statistic. Okay. What would the p-value be close to for this, if you had to guess? There's a certain value that it's going to be really close to. If the area to the left of negative 2.33 is 0.01, what do you think the area to the left of negative 4.7 is going to almost be? 0. Really close to 0. So if I asked you for, not going to do this on the upcoming exam, but I asked you for the p-value here, and one of the answers was approximately 0, you should be able to determine that from kind of thinking about what that test statistic would mean relative to these critical values. Okay. I wanted to say something else here. Now I forget what it was as we were talking. What did you asked me a question and I said I'd come back to it. Oh yes, yeah, thank you. So the only reason I put these arrows is to make the visual easier to see that the test statistic is clearly in that rejection region. You don't have to draw the arrows. In fact, one of the other ways that you can actually do the critical value approach, if you don't want to draw it out, I think it helps to draw it out. But we're always really looking to see, is the absolute value of my critical value, if that's less than the absolute value of my test statistic here, a t-statistic, then I reject, right? And the reason why we do the absolute value is so that we can always use this, so that it works for a right-tailed test, or when we take the absolute value, it gets rid of my negative signs. It would also work for a left-tailed test or even a two-tailed test. So here you kind of can see, I mean, negative 4.7 is larger in magnitude than negative 2.33. So when I take those absolute values, this would hold and I'd reject. Or if I have it drawn out and I just plot the points, I can clearly see it's in that rejection region. So that's the only reason I do it, is just to kind of have a visual that lines up with what we're doing to make it a little bit easier. Yeah, like if I never like drew these out for you, which I don't really have to do, it just told you, just remember this. I don't know, to me it just makes it a little bit harder. Well, now I've got one more formula that I got to remember, it's checking, and if I just draw it out, it's pretty easy to see that it's more, that it's larger in absolute value, right? It's kind of more to the left here, or it's more to the right for a right-tailed test. So really, it's just a tool for thinking about these better and making sure you're kind of getting to the right answer. All right, any other questions on this before I kind of go back? Okay, so I kind of have a reminder, just synopsis slide of the steps for the p-value in both the critical value approach. I've got some